Physics problem time. Lucy is a spacecraft. And it's going, this is real. I looked it up. So, and Wikipedia may be lying to me, but it's going to fly by, not technically fly, which includes air. It's going to move past 52246 DonaldJohanson, which is an asteroid. Okay, so I looked up as much as I could, but it doesn't really matter. We're going to do it anyway. So I did make some artistic license decisions. So, but here's my asteroid, 52246 DonaldJohanson, which is what I'm going to refer to it every time I say it. Not. It has a 4-kilometer diameter, so I'm going to assume it's spherical. And then from that, I estimated the mass based on the density of rock. So I got the mass at 1.67 times 10 to the 14th kilogram. So then I have spacecraft Lucy flying past it like this. And let's say that it comes the closest approach of 3 kilometers and has a speed of 8 kilometers per second. The mass is 800 kilograms. Number one, and this is just like a homework problem, but different, better, more modern. Number one, what's the change in momentum of the spacecraft Lucy? And number two, how much will it be deflected by? So why would it be deflected at all? Where's my red pen? Got it. Okay, so let's just say that at this point right here, the spacecraft's at this point, then there is a line connecting those, and there is a gravitational force pulling on it that way. So it has a momentum this way and the force on it that way. That's going to cause it to change momentum. It's going to change momentum in the direction of the force because of the momentum principle. So it's going to move down, and the whole path is going to be something like this. Now, these two ends, as it gets further away, the gravitational force gets very small. So at some point, we can kind of neglect that gravitational force. We're going to have to make some approximations here. And we will make some approximations. Because I don't want to, and I will do it the full way too. I'm going to do it two ways. We're going to do the approximation way, and then, of course, the Python way, which is just for fun. Okay, this problem is just a bonus after the problem. So let's start off with the momentum principle. We're looking for the change in momentum of this. So the momentum principle says the net force is equal to the change in momentum with respect to time. And in this situation, the only force acting on the spacecraft is the gravitational force between these two. So suppose I could put this at the origin, but I'm not going to. I have the position of the asteroid. I'll call it R 55246 DonaldJohanson. Actually, it's called RD for Donald Johanson. And then I have the vector location of the Lucy, RL. And then I can find this vector like that. I'm going to call that just R. So if I calculate the vector R, which I could do, R is it's going to be R Lucy minus R DonaldJohanson. Then I can use that to calculate the gravitational force, Fg, negative G, mass of Lucy, mass of DonaldJohanson. It is kind of fun to say. Over R squared, R hat. And so, but you see that we have a problem here, right? I can calculate this gravitational force, but even if I consider some small window of interaction right there, it's going to change direction and it's going to change magnitude. So let's not do that. Let's make this as simple as possible. Let's calculate the gravitational force. Let's call this the X and the Y direction. Let's calculate the gravitational force at that point. And then I'm going to assume, let's just pick, if this is 3 kilometers, let's say it goes from a distance of 1 kilometer over which there's a force. That's just an estimation. Okay. It goes over a distance of 1 kilometer, and the speed doesn't really change. I mean, this is a very weak force. So then I can use that to find the time. Okay. So let's do this first thing one at a time. I'm going to start with the new sheet of paper. And I'm going to calculate the gravitational force. So here is my asteroid. Here is my Lucy. And so this is, I said it has a closest approach of 3 kilometers, or 3 times 10 to the third meters. So let's calculate this force, F. So, and I don't really need to do any crazy vector stuff because I'm making an approximation. So I have G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And then I have that distance. And then I said I had the mass of Lucy was 800 kilograms. The mass of DonaldJohanson was 1.67 times 10 to the 14th. And that might seem like a large mass because it is. It's a giant 4-kilometer diameter rock, but it's nowhere near the mass of the Earth, right? Okay, so I'm going to just write the magnitude of this force, Fg, as G md ml over r squared. So r is going to be, it's this. This is r. That's my scalar value. Let's just calculate this. I'm going to put in my numbers. 6.67 times 10 to the negative 11th. I'm not going to include units. 1.67 times 10 to the 14th. Not going to include units. 800 over 3 times 10 to the third squared. Put it in an actual real calculator. Put it right here. I'm trying to avoid the glare, but then I want to see what. Okay, if I do it right there. Okay, enter, clear. 6.67, use your scientific notation button, negative 11 times, if you do that, if you use your scientific notation button, then you get this treated as just one number, so that's really helpful, times 1.67 scientific notation 14 times 800. I don't have to worry about the unit vector because I'm just finding the magnitude, divided by, now if I use my scientific notation button, I don't have to put this in parentheses. 3e3 squared. Enter. And I get, well, that's not very big, 0.99 newtons. Now let's write that as a force, even though it's not super important. So I'm going to have the force in the negative y direction, 0, negative 0.99, 0 newtons. Now, in order to use momentum principle to find the change in momentum, delta P, I need delta T, right? This is going to be F times delta T. So I need delta T. So let's say that this distance is 1 kilometer over which I care about. And I already said the velocity, the magnitude of the velocity was 8 kilometers per second. So if I use that, let's call that the x direction, and that's the velocity in the x direction, I can say Vx is delta x over delta t. So delta t is delta x over Vx, or 1 kilometer over 8 kilometers per second. See, I don't even have to convert units, right? So I just get 1/8. So now I know my delta t. I can find delta p. Delta p is going to be the force, 0, negative 0.990 newtons, times delta t, which is 1/8 seconds. So I can do that. Delta p. All I have to do is divide 0 by 8, this by 8, that by 8. So I only have to do that middle one. So let's just do that. Divide by 8 equals. So I get 0, negative 0.12, I'll leave it at that, 0 kilograms meters per second. That is in meters per second, right? Because of the way I did that. So that's my change in momentum, which is not very large. Let's go ahead and calculate the change in velocity, right? Because if I divide this by the mass, I get the change in velocity. So I'm going to say, I'll just divide by 800. And I get 0, well, that's small. 1, 2, 3, 4. Negative 1.5 times 10 to the negative 4, 0 meters per second. So super small, super tiny change in velocity as it passed by, which is good, right? Because that means that this approximation that's moving in a straight line and doesn't really get closer is valid. How much closer does it get during that time? Not much at all. But what about the deflection? Okay, what's the deflected angle? So that's what I want to know, how much the deflected angle is. So let's say here is my initial momentum, P1, and it's going like this. And then later, it has a new momentum, P2, which is P2 is that's equals P1 plus delta P, right? Because delta P is P2 minus P1. I can just solve for P2. I already know delta P. I know P1. I can find P2, the final momentum. Now I just want to find the angle between these two vectors. And so I'm going to use a little cheat here. It's not true, but it will work. Well, actually, I do know that. I do know this. Now it's a right triangle, right? Because I know this is my initial momentum. Delta P is my opposite side, and that's my hypotenuse right there. So I can say tangent of theta, I don't even need to find P2. It's going to be opposite over adjacent. So it's going to be delta P vector over P1. Now, oh, I'm sorry, that's not true. I need to write this as a y component. So this is delta P y dot y, I'll put y, over P1 x. I can't divide vectors. So if I do that, this is going to be, theta is going to be equal to the inverse tangent of the change in momentum, which was 0.12, I'm just using the positive value, 0.12 over the total momentum, the momentum in the x direction, which was, I didn't calculate. This is going to be equal to 800, the mass, times the velocity in the x direction, which was 8 times 10 to the third meters per second. And that's the initial momentum. So this is going to be a super tiny angle, and it's probably not even worth calculating. But clear, so I'm going to say inverse tangent of 0.12 divided by parentheses, because I need these multiplied together, 800, the mass, times 8 scientific notation e to the 3, close parentheses, close parentheses. And I get 8.95, 1, 2, 3, 4, 5, 6, times 10 to the negative 7th degrees. So super tiny. Okay, bonus time. So if you want to stop here and go on with your business, I support that. But I'm not going to go on with my business. I'm going to actually model the exact same situation and see if it's true. So I'm going to have an asteroid. I'm going to have a spacecraft. So this is going to be, I'm going to put that at the origin, but it doesn't really have to be. And then I'm going to calculate the vector force each instant in time, well, in time intervals. I'm going to break this into a time step of, see, I had it pass by in 1/8 of a second, right? So let's say delta t is 0.01 seconds. That should be fun. What am I doing? Okay, and so during that time interval, I can calculate R. R is R Lucy minus R DonaldJohanson. And then I can use that to calculate the force, F negative G, mass of Lucy, mass of DonaldJohanson, R hat over R magnitude squared. And then I can use that to update the momentum of Lucy, P2, P1, plus F, which I just calculated, delta T. And then I can use that to update the position. R Lucy 2 is R Lucy 1 plus P2 over mass of Lucy, delta T, and then update time. So this is my standard numerical recipe, right? This is the Euler method of numerical calculation. So I'm going to build all this in Python in 3D, and let's just see what happens and see if it's even fun. Okay, jumping over here to my computer. Okay, I already calculated the mass. I already told you that. That's fine. Let's make DonaldJohanson. I'm going to call it DJ. It's going to be equal to sphere let's put it at the origin. Position equals vector 0, 0, 0. The radius is going to be equal to 2 kilometers. That's what I said, 2e3. That's all I need. Run that. So there it is. Yay. Now I'm going to make Lucy with capitalized is also a sphere. Position, so I want to have it up 3 kilometers and over half a kilometer. So it's going to be, the position is going to be dj.pos plus vector negative 0.5 e3. What did I say? It was 3 kilometers away? Yeah, 3. 3 e3, 0. So I'm going to add it to that. Even though it's at the origin, that's fine. And I'm going to give this a radius of, if I give it a radius of, something realistic, you won't be able to see it. So let's say the radius is 100 meters. Let's try that. And color equals color.cyan, yellow. I like yellow. And then make trail equals true. Let's run that and see if we can see it. Okay, there it is. That seems not right. If it's 3 kilometers away, is that what I had? It seems like it's too close. 3 kilometers away and 2. Okay, that's fine. Just go with it. Just go with it. So now we already have the mass of DonaldJohanson. The mass of the Lucy, I'll just call it LM, is 800. Now I need velocity. Velocity, let's just do it like this. Lucy.v is vector. It's going in the x direction. And it's going to be equal to, what did I say it was? 8 kilometers per second. So 8e300. And the momentum, Lucy.p, is equal to the mass of Lucy times the velocity of Lucy. There. All set. So now let's say t equals 0, dt equals 0.01. Let's run this for a very short amount of time. So because it's only going to take 1/8 of a second, so let's run this for 0.2 seconds. So while t is less than 0.2, rate of 50. So I'm only going to do 50 calculations because otherwise you just zoom by too fast and we'd miss all the fun, and we don't want to do that. Number 1 step is to calculate r. R is equal to Lucy.pos minus dj.pos. No, not opos. Now I can calculate the total force. So F equals negative g. I don't have g. Put it up here. G equals 6.67 times 10 to the negative 11th. G times ml, no, ml times md, that's what I called the mass, times norm r, so that's the unit vector pointing in the direction of r, divided by mag r squared. Now I'm going to update the momentum of Lucy. So Lucy.p equals Lucy.p plus f times dt. Now I'm going to update the position of Lucy. Lucy.pos equals Lucy.pos plus Lucy.p times dt divided by ml, right? I need to get the velocity, so the momentum divided by the velocity, the mass is the velocity. Now I'm going to update time, and that should be it. So let's just run this and see what it looks like. It won't look like much. Yeah, that's it. So just okay. Let's move it back even further and make trail. Oh, aha! That's why I didn't leave a trail. Let's move it back further. It shouldn't really change the outcome too much because the gravitational force is so small. Let's move this to 2.5 and let's run this for 1 second. Okay, nothing that you can see really. I'm going to go ahead and calculate and print the deflection. So let's say P1 is equal to Lucy.p. I need to write that because I'm going to change the momentum throughout the whole time and I want to calculate the difference. So let's put this as dp at the end of the thing. dp is going to be the final momentum, which is Lucy.p because it's been changing, minus initial of P1. And let's print that. dp equals dp kilogram meters per second. And remember what we got before. Let's see if we get something similar at least. It won't be the same because we did it differently. Okay, so I have a momentum, change in momentum of 0.56. Now, if you look at what I did before, I got negative 0.12. And that's different, but it's not that different. It's not that different, right? It's still less than 1 kilogram meter per second. And that's the important thing. It's the same order of magnitude. It's a great way to get a rough order of magnitude estimation. How can we make a better estimation? Well, what if we take a longer time window over which the force acts? That might be more reasonable. What if we broke it into multiple steps? You know, big steps, 3 different steps. We could do that. This is still an estimate, right? Because I'm still assuming the force is constant, just over a smaller time window, and I'm doing it more times. But this is actually pretty important because we don't really know the mass of DonaldJohanson 255246. And one of the ways we can find that out is to fly a spacecraft by it. Look at the deflection, and by looking at the deflection, now we know something about the mass of that object. Because we can't put it on a scale or anything like that. That's how we do stuff in space. Okay, that's the end. Hope you found that useful.